color is metal? If you're thinking gray or silvery white, you'd be correct for over 90% of the elements on the periodic table. What about the other 10% though? One exception you may have thought of is gold. But what exactly makes gold shiny yellow instead of white? In order to answer this question, we need to start by taking a look at the atom. In each atom, there is a positively charged center, or nucleus, with some number of negatively charged electrons farther out. These electrons move rapidly within different regions of electron density called orbitals. Typically, the orbital shells each have different energies, which we can envision like steps. When an atom of gold is given a push of energy matching the step height, an electron occupying this lower energy orbital gets excited to this higher energy state. The colors we see are related to these transitions. Each color of light actually has a different associated energy on the electromagnetic spectrum. Sunlight, or white light, contains light of all colors in this section of the spectrum. Metals with very large step heights appear white or silvery, since all visible light colors are reflected back. But when the outermost step height matches that of blue light, for instance, that color is preferentially absorbed by the metal. The light that is reflected back into our eyes would have less blue than the other colors in it. The material would appear to us as the complementary color, yellow. This works wonderfully for most metals. But hold on a second. It doesn't fully account for gold's yellow color. In fact, based on this model, blue light simply doesn't have enough energy to push up gold's outer electron. To explain this discrepancy, Einstein's theory of special relativity saves the day. Gold, with its 79 protons, exerts a massive attractive force on its innermost electrons. These electrons must move over half of the speed of light to avoid falling into the center. At this speed, special relativity tells us that the electrons actually gain mass. The increased mass means that the fast-moving electrons must fall in closer to the nucleus. These electrons are now stabilized by their increased attraction to the nucleus and are now at a lower energy. But not all orbitals are created equal. For gold, the first possible energy transition is from a d orbital to an s orbital. S orbitals are spherical and have more electron density near the nucleus. These orbitals are heavily contracted by relativity. D orbitals, on the other hand, are shaped like several dumbbells and have more electron density farther from the nucleus. These electrons are on average too far and thus move too slowly to be affected significantly by relativity. These combined effects lower the energy step height, allowing gold to absorb blue light. This is what gives us the familiar golden appearance we all know and love.